Welcome! In this video, we will compare the energy behavior of constant air volume (CAV) and variable air volume (VAV) systems and understand why and when each is appropriate in practice. We will cover 5 segments. First, the control logic of CAV and VAV. Then the energy balance that governs system behavior, followed by per load traits for each system, and finally selection guidance selection guidance grounded in load variability and ventilation requirements. By the end of this video, you are going to be able to compare the energy or how CAV and VAV respond to per load and what that means for coil and reheat energy. Second, you will apply the energy balance to quantify how ventilation and latent loads influence performance. And third, we will judge when each system is a better fit, considering load variability, humidity management, and minimum ventilation needs. These are directly aligned with the intended learning outcomes of this module. This slide here, I want you to start thinking in the next question. Which system uses less energy at per load? A CAV system that holds airflow constant and adds reheat, or a VAV system that reduces airflow to meet the sensible load? So which system uses less energy? Think first about what is kept constant in each case and which terms in the energy balance are affected. Consider the cooling coil energy and reheat separately. In CAV, the coil exit temperature is held roughly constant and airflow is constant, so the coil loads tend to stay high and reheat increases as the sensible load drops. In VAV, as you can remember, the coil exit stays low for the humidification, but airflow falls with the load, lowering coil and fan energy until the minimum flow threshold. Keep ventilation in mind also. Both systems, CAV and VAV, must meet minimum outdoor air, but VAV can reduce recirculator flow as the sensible load falls. Reflect on CAV energy stays flat for the coil and increases for reheat, and the VAV energy tracks the sensible load until reheat is needed at the minimum flow. So think about all of this, and we will explain more concepts in this video. When discussing HVAC systems, it's essential to understand the difference between constant air volume (CAV) and variable air volume (VAV) systems, as they control loads is fundamentally in different ways. They control loads in fundamentally different ways. The key distinction lies in how each system adjusts to changing thermal demands within a space. In CAV, the supply airflow is fixed, and the coil provides a low leaving temperature to handle latent loads. As sensible load drops, some temperature is maintained by reheating the cool air before it enters the space. This delivers stable temperature and humidity, but can be energy intensive. In VAV, the supply temperature is held roughly constant, while the airflow is throttled to track the sensible load, so the airflow is changing. Reheat is needed only when the zone is at or below the minimum flow required for ventilation or air movement, because if you give too much airflow that is cold, you're gonna cool the environment below the comfort zone. So you need to reheat this air before it enters the zone. This typically reduces coil and fan energy at per load. Because the humidification occurs at the cooling coil, both systems may target similar coil leaving conditions. However, fan power falls with flow in VAV, and IAQ requirements set a minimum supply rate. Shaping reheat becomes necessary. This means that in VAV systems, you need a minimum flow because of indoor air quality conditions, to keep a good indoor air quality conditions. So building on our discussion of how CAV and VAV systems handle loads, let's now delve into the fundamental principles that govern their operation, the energy flows and the key balance. An essential concept for understanding HVAC systems is the energy balance, which dictates how different energy flows, including sensible and latent loads, reheat and ventilation, must sum up to the total load handled by the cooling coil. This relationship is crucial for analyzing how systems respond to changing conditions. So the governing balance for the Airside equation is the one that you're looking at in the screen. So here the LS and the LL are the sensible and latent zone loads, and QRH is reheat. And the last term is the ventilation contribution from mixing outdoor air with return air. Then the ventilation term, that is this MA times the enthalpy difference, captures the energy to cool and humidify the outdoor air before it is supplied. Then humidity outdoors is high. This term can dominate. Notably, air does not accumulate, so ventilation flow equals exhaust, and the mixed air state sets the coil inlet. So this means that the zone does not accumulate air, so this MA is going to be constant in the system. So we have that under CAV with the fixed airflow and the coil exit temperature. The coil is largely set by the ambient ventilation and remains nearly constant. Reheat then increases linearly as sensible load decreases. This behavior is central to CSV per load penalty. So this means that with CAV we have this issue of nearing the reheat, when the sensible load is changing. Well, now that we established the governing energy balance, let's apply it to understand the per load behavior of a CAV system. This will help clarify why these systems, despite offering excellent control, are often associated with high operating costs when loads fluctuate. In CAV, because airflow and coil leaving temperature are held, the flow is constant, the coil leaving temperature is also kept constant, then the coil energy changes little with some sensible load at a given ambient, while reheat rises as LS falls. So as the sensible load of the zone is falling, the reheat that is given to the air is going to increase to keep the same ambient conditions in the zone. This is a classic CAV per load penalty. So the benefit of doing this cooling and reheating is tight temperature and often humidity control, because the coil can be kept cold and downstream reheat trims the supply to comfort. The trade-off is significant reheat energy at per load, leading to high operation costs when loads vary. Thus, CAV is generally reserved for zones with steady internal loads or applications demanding precise humidity control, where the operating penalty is justified by performance requirements. Having explored the per load behavior of CAV system, let's now turn our attention to the per load behavior of VAV systems. We will see how these systems' ability to modulate airflow leads to significant energy savings, particularly in buildings with fluctuating loads. In VAV, the airflow is modulated, so to meet the sensible load, while the coil leaving state is kept low for latent control. So the coil leaving state is fixed to control the latent load, the humidity levels, the humidity ratio, and what the system modulates is the airflow. So consequently, the Q coil decreases with load until the minimum flow threshold is reached. So then reheat is generally unnecessary above minimum flow because you are regulating with the changing of airflow. Once the sun reaches minimum flow, and remember that this minimum flow is set because you need to keep a flow to keep a proper indoor air quality. So when the sun reaches the minimum flow, then reheat may be introduced to prevent overcooling while satisfying ventilation. So because fan power scales down with flow and the coil duty falls as well, VAV typically achieves significantly lower operating energy over the annual load profile of office-type buildings. Having examined the distinct behaviors of CAV and VAV systems, we can now address a critical question. How do you choose between CAV and VAV in practice? The decision ultimately comes down to matching the system's operational characteristics to the specific needs of the building and its occupants. In diverse variable load buildings, VAV tends to best align with energy and fan power savings while maintaining comfort and indoor air quality via minimum flow and the cold coil. So, and in near constant load, suns or critical humidity environments, CAV can deliver stable conditions with a reheat, though at a higher operating costs because this cooling and reheating. This trade-off is common in labs, healthcare, or data-heavy spaces. Always check that ventilation, lighting control, and reheat or airflow limits are feasible for your chosen approach. To wrap up our discussion on constant airflow CAV and variable airflow VAV systems, this final slide serves as a concise summary of the key takeaways from our analysis of their operational difference and per load behavior. It highlights the core principles you should remember when choosing between these two approaches. CAV provides stable conditions but incurs in reheat penalty at per load because airflow and coil set point are fixed. VAV reduces airflow with load, cutting coil and fan energy and avoiding reheat until hitting the minimum flow constraint. This is why VAV dominates in variable load commercial buildings. Always quantify states in the heat balance equation, compute flows and enthalpies, and check indoor air quality and control constraints before selecting a strategy. Before we conclude, let's look at some key concepts that build on what we've learned, offering ways to continue learning about HVAC optimization. Here are some advanced strategies that are essential for achieving even greater efficiency and performance in real-world applications, and I invite you to look at them. To go further, explore CAT reset strategies. You can find information about raising supply air temperature at per load to reduce coil and reheat energy, while still maintaining dehumidification. This concept is used in many optimized CAV-VAV sequences. You could also look into the economizer cycle, which is used to increase outdoor air fraction when ambient conditions are favorable, thereby reducing mechanical cooling and improving energy performance. Finally, consider dual path DOAS ideas, where outdoor air is conditioned separately to handle latent load efficiently. This is used to decouple ventilation from sensible cooling and can improve comfort and energy use. Thank you for watching this video.